Hello Chem 1A, this is Chapter 11, Lecture Video 9, and we're going to be talking about expanded octet hybridized orbitals. Now, this is a little tricky because recently, like within about the last 2 to 3 years, energetics calculations and theory have shown that these types of hybrid orbitals are very unlikely to actually exist. Our textbook still covers them. Our homework still covers them, so we still cover them, but these will eventually be kind of disregarded at some point once the textbooks catch up to the theoretical science. And it just takes some time. So let's go over them as though they exist, but in reality they don't. So in an expanded octet structure, we need 5 half-filled orbitals on phosphorus in order to make, for instance, PCl5. PCl5 has a trigonal bipyramidal structure for its electron group and molecular geometry. And so if we look at its atomic orbital diagram, we know that there are actually only 3 unpaired valence electrons in phosphorus. Now that is a bit of a problem because we need 5 of them to form 5 bonds. So how does this occur? Well, we say, at least right now, is that 3s and 3 of the 3p orbitals and 1 3d orbital now are going to mix together to give us our new sp3d hybrid orbitals. We get then 5 unpaired valence electrons that can then bond with the unpaired valence electron in chlorine and give us sigma bonds between each chlorine and the phosphorus atom. So sp3d hybrid orbitals are going to occur when we have electron group geometry trigonal bipyramidal, and we're always going to form 5 of them in this scenario. So each one of these can form a sigma bond, and let's kind of summarize this. So again, sp3d hybrid orbitals are going to occur when we mix one s orbital, 3p orbitals, and one d orbital together. This gives us a total of 5 hybrid orbitals, 5 sp3d hybrid orbitals. And this occurs when our electron group geometry is trigonal bipyramidal.
Okay, so the last type of hybrid orbital is an sp3d2 hybrid orbital. This occurs when you mix one s orbital, 3p orbitals, and 2 d orbitals together. This will form 6 sp3d2 hybrid orbitals. And this type of hybrid orbital will occur when your central atom has an electron group geometry of octahedral. That's the last type of hybridization, so let's just take a second, go over all of them, right? sp hybrid orbitals occur when our electron group geometry is linear. sp2 occur when our electron group geometry is trigonal planar. sp3 occur when our electron group geometry is tetrahedral. And sp3d occur when our electron group geometry is trigonal bipyramidal. sp3d2 occur, like we're showing here, when we have an octahedral. And so that's all of our hybridized orbitals. So let's do some example problems. Hybridization. One of the things you could be asked, simple multiple choice question is, hey, what hybridization is present on this molecule? So if we look at some of these, if we have XeF4, for instance, the way we do this is you need to figure out your electron group geometry around that central atom. In other words, draw the Lewis structure of XeF4. So if we count up valence electrons, this guy has 8, this has 7 times 4. 7 times 4 gives me 28 plus 8, so that's 36 valence electrons. So if we draw this guy out, I'm going to attach my fluorines. Then I'm going to put my lone pairs on the fluorines to make them have octets. And this structure, I've used 8 from the bonds and 24 from the lone pairs. That gives me 32 valence electrons I've used. I still have 4 more to go. Those 4 need to go on the central atom as lone pairs. This molecule has an electron group geometry of octahedral. How do I know that? Because it has 6 groups of electrons around the central atom. 1, 2, 3, 4, 5, 6 groups total. Means we're an octahedral, which means our hybrid orbitals here are going to be sp3d2. If we look at CH2O, this guy has 12 valence electrons. The central atom's carbon. I'm going to connect all the other terminal atoms to the carbon atom. And then I got to put lone pairs to make octets. Well, the only thing that needs an octet is the oxygen and the carbon. So we're going to put our remaining 6 electrons there. We're out of electrons. Oh no, carbon doesn't have an octet. What do? We got to form a double bond. So erase one of your sets of lone pairs, turn it into a double bond. The electron group geometry here, our EG, is going to be trigonal planar. Meaning this guy has sp2 hybrid orbitals present because that's the type you have when you have trigonal planar electron group geometry. If we look at BRF5, this guy has 6 times 7, so 42 valence electrons here. And we have Br as our central atom. I have used up 40 of my 42 valence electrons. The other 2 go on the central atom. This guy again has 1, 2, 3, 4, 5, 6 groups of electrons, meaning our electron group geometry is octahedral. Or in other words, again, sp3d2. This guy, I don't even have to draw it. I know it's an octahedral, sp3d2. Because there's 6 fluorines, it has to be octahedral. Okay, something that I have been meaning to cover is when and when not to use what we call dashes and wedges. So just to kind of look at this structure here, this is one way to draw it. It's still two-dimensional though, so if we want to try to show some three-dimensionality to our structure, I would use dashes and wedges for some of these. And the way I do that is kind of like this. And this is the structure if we were to use dashes and wedges. The wedges, these guys, indicate that the fluorines are coming out at you off the paper, and the dashes, these guys, indicate that they're going back into the paper, away from you. You should be able to use these to some extent to kind of predict what your shape should look like. If you have questions about it, just please ask me and let me know. All right, let's do, Br3 minus, my bad. We got one more. So I'm going to erase this guy just to kind of give me some space for that. So if I count how many valence electrons this has, Br3 is 21 plus one more because of the negative charge. So this guy has 22 valence electrons. I'm going to take my 3 Brs and attach them to each other. Then I'm going to put lone pairs on the terminal atoms. And if we look at how many electrons I've used so far, I have used a total of 12 from the lone pairs and 4 from the bonds, which gives me a total of 16 valence electrons used. I have 6 more to go. Those 6 have to go on my central atom. This molecule has 1, 2, 3, 4, 5 groups, meaning it has sp3d hybridization because it's a trigonal bipyramidal structure. All right, let's do another type of question. And so I'm just going to kind of draw this question out. One of the things you could be asked to do is to describe what orbitals are overlapping in order to make whatever bonds we have. For instance, let's say I give you that this is the structure of a molecule So let's say I have this structure and I want to figure out, hey, all these bonds are due to overlapping orbitals. And I want you to describe the orbitals overlapping to make each bond. And what type of bond is being formed. So for instance, there's some of these are going to be identical, right? This bond, and this bond, these 3 hydrogen-carbon bonds are all going to have exactly the same orbitals overlapping and are going to form sigma bonds. This is a unique bond. So I'm going to just number them as a different color for each one I need to describe. So this is all 1. This is the second bond I need to describe. This is the third bond I need to describe. This is the fourth. This one is the same as the other one across the way, so I'm not going to describe it twice. This one's the fifth. And I'm trying to find another color here. This one's the sixth. Ooh, that's ugly. Let's go darker red. This is the sixth. So we have 6 different bonds that we have to describe out. So let's talk about that first one. 1, right? This is due to the 1s orbital on hydrogen overlapping the sp3 orbital on carbon to form a sigma bond. I know that because this carbon has a tetrahedral electron group geometry, which means it has sp3 hybrid orbitals around it. Number 2 is due to the sp3 orbital on carbon overlapping with the sp2 orbital on, I'm going to say this is carbon 1, we'll say carbon 1, and this is carbon 2, on carbon 2. This also forms a sigma bond. So let's talk about number 3. Number 3 is going to be 2 parts. One of those parts is that we have an sp2 on carbon 2 overlapping. We'll call that one carbon 3. So sp2 on carbon 2 overlapping with sp2 on carbon 3. Again, we get a sigma bond here. There's also a pi bond though, and that's formed by overlapping a p orbital on carbon 2 with a p orbital on carbon 3. And this needs to be somewhere stated that it's a side-by-side overlap. That's how we get those pi bonds. Next, we can kind of talk about number 4, right? This is going to be the 1s on hydrogen with sp2 on carbon for both of those carbons, carbon 3 and carbon 2. Let's talk about number 5. I'm going to do it up here because I'm running out of room down there. This is going to be the sp2 on carbon 3 with the sp3 on oxygen, and it forms a sigma bond. And finally, we have number 6. This is going to be sp3 on oxygen with 1s on hydrogen, forming again another sigma bond. And so this is something you need to be able to do, describe each one of the overlaps that is forming a bond in a structure. And I'd give you the Lewis structure like I did here and just basically ask you, hey, describe what orbitals are overlapping to make each of these bonds. You don't need to repeat ones that are going to be identical, right? All the carbon 1 bonds with hydrogen are going to be identical statements, 1s with sp3 on the same carbon. So if you have any questions, as always, please contact me. I'm always happy to help.